Hi everyone. This is a review of kinematics and dynamics. So we've got 3 weeks before the AP exams, and so I just want to make probably a couple videos to go through some different things. So kinematics is motion and describing motion, its position, velocity, all that sort of stuff. If you don't know the definitions of these words here, make sure you do. They are commonly used terms, and so you need to know them. When it comes to constant speed, we don't do much with constant speed, but we do have things that move that way. So we know distance is speed times time. I'm not sure if that's on your formula sheet, but our most often we have uniform acceleration type questions, and for uniform acceleration questions, we have those equations that we typically use. Make sure that you know what's on your AP formula sheet. So it's going to be your job when you take the AP exam to print out the AP formula sheet and have it with you. That is one of the resources you will be expected to have. Okay. So uniform acceleration, a special case of that is free fall. And we know everything falls at the same rate as long as air resistance is negligible. Okay, so if the term free fall is used, that is the assumption, is that air resistance is negligible, which means, of course, it doesn't matter. It doesn't matter what the mass is. If we have two things, little m and big M, and they both drop from the same height, they will fall at the same rate. So halfway down, they'll take the same amount of time there, and so on. So they will both fall at the same rate, and that rate is called the acceleration due to gravity, which we symbolize by little g, and that's 9.8 meters per second squared. But be aware, on the AP exam, you can use, if you need to do a calculation, you can round that to 10, and that is perfectly acceptable and may make things go a little easier. Instead of having to get out your calculator, doing things with 10 makes things much easier. Also remember that on the way up, if you throw something upward, that on the way up, let's say that we toss something upward and it has an initial velocity of, say, 30 meters per second. Then 1 second later, if we make this kind of like a strobe photograph, so 1 second later, so this is t equals 0, at t equals 1, its velocity is going to be 20 meters per second. And then at t equals 2, it's going to be going 10 meters per second. And of course at t equals 3, the velocity is going to equal 0. Okay. So remember, that's what free fall is all about. And then we have projectile motion. And that's a combination of two types of motion: the horizontal motion, which is constant speed, and the vertical motion, which is uniform acceleration. And so we have, so if you have a ball that's tossed and it undergoes projectile motion, it makes that nice parabola. Okay, its velocity at any particular time is v, but that has a horizontal component that we call vx, and a y component, or a vertical component, we call vy. And so later, as it moves upward, so vx in this context is going to be the same the whole time. It's constant. It's always traveling the same distance each second horizontally. But as it moves upward, that vy component, gravity's pulling it down, so it's slowing down on the way up. So vy gets smaller, and there at the top it still has vx but no vy, and on the way down we still have vx, and vy would now point downward, and so on. so you know that. Remember some important things to remember when you're solving projectile problems. We know that the y component of the velocity is 0 at the top. We also know that we can use symmetry. So if you have something like this, when it's at the same level, it has the same velocity, just the sign has changed. So if the upward component here is like 15 meters per second, then the downward component here, when it reaches that same level, is also going to be 15 meters per second. And in terms of velocity, we include the negative sign for the direction. Okay. So that's a quick review of that. I know you can all solve problems, but one of the things that we're doing is we're going to try to kind of focus on what the AP test is going to be like this year, and that's going to be a bit different. So you're not going to have to do a lot of calculations, from what I understand here. So it's not a matter of that. We want to look at things in kind of the broader perspective here. So the graphs turn out to be really important. And so the graphs, we have position versus time, velocity versus time, and acceleration versus time. And from these graphs, we should be able to determine what the displacement of the object is, the speed, the direction, and the acceleration. Now, each graph will not be able to tell you all four things, so we have to be a little bit careful there. So if we have something like this on the position versus time graph, so let me put a scale on here. Let's say that's 2 and 4. Make that. All right, so displacement. How do you get displacement? Actually, this would be one of the times I'm going to ask you. You might want to actually pause your video for a second and think about these. If you could fill these in, take a second to think about it. That would be a better way to do it than for me. If I were in class, I would put the pen down, give you 5 minutes to fill that in a bit and discuss with your neighbor. So right now, if you want to pause the video for a minute, I would do that and see what you can remember about these, which parts you could fill in, and then in about 5 seconds I'll start and give you the answers. So pause now. Alright, so hopefully you remembered some of this. Alright, so displacement, remember, is change in position, so that's really easy. So we're going to take the final position minus the initial position. You're just going to look on the graph and look at the final position and the initial position. So in this case, the final position looks like it's about 3. The initial position is basically -1. Okay. So speed and direction. So speed and direction, remember that on this graph, we know that slope equals velocity. And velocity contains both speed and direction. Okay. So the speed is equal to the slope. We look at the steepness of the slope. In other words, the number. Okay, so a horizontal line is 0 slope, so that's 0 speed, is not moving, position remains unchanged, and the steeper it is, the more distance it's covering each second. So the direction, remember, we're thinking of an object moving along a number line, so our two directions are positive and negative. So the direction is the sine of the slope. And then the acceleration is given, basically we can't come up with a numerical value for the acceleration from here, but we do know if something's accelerating, its velocity is changing, which means the slope is changing. So we do know that if we see a curve on a position versus time graph, a curve will have changing slope. A straight line has constant slope. So acceleration, we can see if we have a curve, and then we know that the object is accelerating. All right. So for a velocity versus time graph, and the velocity versus time graph I'm doing here is not necessarily for this position, this particular position versus time graph, so I'm just kind of speaking in general. So if we have a velocity versus time graph, it might look, say, something like that. Okay. All right, so displacement, if you remember, for displacement, you look at the area for the velocity versus time graph. And I always put under. The graph, I put quotation marks around the under because we want the area between the velocity graph and the t-axis. And remember that this is positive area, and anything below the axis is negative area. So that's how you get displacement. Speed is just the, you just look at the graph, get V from the graph. The direction is again the sine of the velocity. So the sine of the velocity is basically anything above the t-axis is positive. It's moving in the positive direction, and then when the line is below the t-axis, that's negative. Okay, and then the acceleration, remember acceleration is equal to the change in velocity over the change in time. So on a velocity versus time graph, that's equal to the slope. So the slope equals the acceleration. All right. So we can get a lot from a velocity versus time graph. It's significant. I think the number of times where they ask you to interpret these, I think it goes to a little bigger depth, greater depth of understanding. So you're likely to see something like that. Now when it comes to an acceleration versus time graph, there is no way to get the displacement from that. It just doesn't work. Okay. When it comes to speed and direction, here's what I will say. If you have an acceleration versus time graph, and our acceleration versus time graphs are all going to be horizontal lines basically. And again, here's a case where this graph does not correspond with either of those two graphs. I'm just doing this in general. Okay, so when it comes to speed and direction, this is kind of tricky. So we know that the area, so like velocity versus time, the area is equal to the change in position or displacement. So the area under an acceleration versus time is equal to the change in velocity. So the area is equal to the change in velocity. Which kind of gives you, in terms of speed and direction, we need some more information. You can't just look at an acceleration graph and tell which direction it's going or how fast, but you do know how much it's changing. And they could, if they give you an initial velocity and they ask you what the velocity is later in time, then you could figure out the change in velocity from the area. And if you know the change in velocity and the initial velocity, you can come up with the final velocity. So the acceleration is basically, we look at that, so A from the graph. It's pretty rare to have to go backwards with the acceleration graph. So it's fairly common to maybe get an acceleration graph from a velocity graph, however. Okay, so this is another place where I'm going to ask you to go ahead and pause the video for a minute. And what I would like you to do on the next 3 slides is I have given you one of the graphs, and then I want you to go ahead and figure out what the other 2 would look like. So in this one, I've given you the velocity graph, and in this I want you to draw the velocity graph for this particular position graph and the acceleration graph for this situation. So on slides 4, 5, and 6, I want you to do that. So this is another case where you should pause the video and go ahead and do as much as you can. Like I said, if we were doing this in class, I would tell you to talk to your neighbor if you want to. But go ahead and try that, and then when you're ready, restart the video, and I'll walk you through some of this. So go ahead and pause the video. All right, we're back, and so let me kind of step you through this. So I kind of filled in what's here already. So from the position versus time graph, we can see the displacement. I'm looking for the whole graph. So we've got 2 minus 0. Remember, all we care about is final position and initial position. Okay. By the way, if they asked you how far the object moved, the distance that it traveled, it went 4 meters there, and then back 2 meters. So that's a total of 6 meters that it moved, but its displacement was 2. Okay. So speed, we're looking at slope. Remember, you can't just necessarily count boxes because you have to look at the scale there. So if you go 4 meters in 2 seconds, so you're going 2 meters per second there in the first part, and -1 meter per second in the second. So the direction, we're just looking at the sign, so it's moving in the positive direction initially, positive slope, positive direction, negative slope, negative direction. And the acceleration, we are ignoring this really sharp instantaneous change in velocity there. So since it's all straight lines, we know there's no acceleration there. So now if we look at this on our velocity versus time, so let's go ahead and construct the velocity versus time graph. So we've got, for the first 2 seconds, it's going 2 meters per second, and then for the next 2 seconds, it's going -1 meter per second. And for the displacement, let me just show you that from this graph, we would look at the area. Delta x is equal to the area. So that would be this area here and this area here. And so we'd have 2 times 2, and then we're going to subtract 1 times 2, and you'll notice that we get a displacement of 2, and these should always agree with each other. If you get different answers for those two, you did one of them wrong, or maybe both. So the speed, we can see that this is very clearly what we would get right there. So we've got 2 meters per second there, -1 meter per second for the second part. So for the direction, we can see that we are above the t-axis, so we have positive velocity for the first 2 seconds and negative velocity, so that sign is what tells you what direction you're moving in. And the acceleration, again, there is none because there's no curve. So our acceleration graph would look like this. So I'm not going to be concerned about finding displacement or speed or direction from that graph. You can't really do that. Okay, the next slide is this one. So now we're starting with a velocity graph. Okay, and if we start with a velocity graph, so the displacement here is 0 because you can see that we have an equal amount of negative area and positive area. So after 4 seconds, the object is going to end up at the place it started if its displacement is 0. So I'm giving you this as the initial position. So we know it's going to end up there. Okay. If we look at this, so the velocity is constantly changing. So this is slowing down because the velocity is getting closer to 0. So it's slowing down for the first 2 seconds and then speeding up for the last 2 seconds. And we know it is traveling in the negative direction for the first 2 seconds in the positive direction. So we have slowing down in the negative direction and then speeding up in the positive direction. So if we go to create this position versus time graph, slowing down means the slope is getting closer to 0 or closer to horizontal, and then it's going to start speeding up. And at 2 seconds we would have a slope of 0. So that would look some sort of curve, something like that. Now exactly how far down that goes, that doesn't matter. So this is kind of a qualitative sketch. We know that the initial and final position have to be the same. So your curve could be steeper and end up with something like that. But we do want this thing as a parabola opening up, and those two in the same. Okay, so displacement we know is equal to 0. Okay, and then we could again sort of fill these things should be consistent with each other. Now looking at it on this graph, so speed we have negative slope and negative slope that's getting shallower. So right here at t equals 2, you can see that the slope would be 0. It's a horizontal line. So we're going from steep negative to 0, so that means it is slowing down, and then from 0 it's getting steeper again, so that is speeding up. And then the direction, negative slope for the first part, positive slope for the next part. Alright, so the acceleration, yes, we have a curve, so we know there is an acceleration there. We can't come up with a numerical value from there. Okay. So our acceleration graph, as we look at this, so the acceleration, we're going to look at the slope is equal to 1 meter per second. So if we have 2 and we have 4, and our acceleration graph, so this is going to be uniform acceleration of 1 meter per second per second. And it's going to be positive because the slope of that line is positive. Okay. Displacement we can't do. Okay. Let's just do the change in speed if you want to look at that. So the area is equal to the change in velocity. Sorry, change in velocity is a better way to say that. So with that area we've got 1 times 4. So the change in velocity is positive 4. So if you look at that, it started at negative 2, ended at positive 2. So it changed by 4 meters per second. That was the change in velocity. Direction, we can't say what direction the object is moving from the acceleration graph. The acceleration itself we know is 1 meter per second. Alright, our next slide here. So in this one I gave you a position versus time graph that's a curve, and so when it comes to the velocity and acceleration we can do them qualitatively, meaning that the numbers here really don't matter. We're looking for the general shape. So if we look at this displacement, so we want a velocity graph, it should have negative displacement. It is traveling in the negative direction and is slowing down. Okay, so negative direction, slowing down. So we're going to start here with negative velocity, and the negative velocity is going to have to get close to approach 0. If you look at this, it tends to be basically be horizontal there. So I'd be okay just drawing something like that. So that would show negative direction. It would be negative displacement because it's below the t-axis. It's slowing down because the velocity is getting closer to 0. It's in the negative direction because we are below 0 for the below the t-axis there, and it is positive acceleration because we have a positive slope on that line. Okay, and then for the acceleration graph, if we're doing this again, this is a qualitative, so we want constant positive acceleration. So it'll be a horizontal line in the positive area, and that's all you have to do for that. Alright, so that's a quick review of kinematics. Now let's talk about dynamics. So kinematics is all about how things move, and if you know things about like initial velocity and so on, then you can predict where it might be in the future and so on. So dynamics is explaining that motion. So dynamics really is about Newton's basically first two laws. The third law is important, may come up, of course, but I really want to focus on the first two. And the big thing about the first two laws is they relate the forces on the object to the way they move, to their state of motion. Okay. So the motion can either be rest, constant velocity, which is straight line at a constant speed, or accelerating. Those are the three possible types of motion. And the first law says that if there's no net force or no unbalanced force on the object, then it's either at rest or moving in a straight line at a constant speed. Okay. And so the rest is obvious. We took our little pucks over to Flannery, so if you remember that, kind of constant speed, no friction. So it's not that there are no forces on the puck, but they balance out. You had the upward force from like the air on the puck and the downward force from gravity balancing each other out. So the net force was zero, but the object could still be moving. It was moving in a straight line at a constant speed. So that's the second law. So dynamics is really important, and there are lots of different ways to ask the questions. So we want to be careful about the strategies. So one thing when it comes to strategies, make sure you identify the state of motion, because that tells you something about the forces. Drawing a good force diagram is really essential, and then you can use the state of motion and the force diagram to generate equations if you need to do that. So let me show you a couple situations here. So example one is static equilibrium. So we have this sign hanging from these strings, and we want to go ahead and go through the strategy here. So the force diagram, when you draw the force diagram, okay, we're going to have a weight force downward equal to mg. We'll have a tension force this way, T1, and we'll have a tension in that direction, T2. Okay, they will usually give us an angle, so let's call that angle theta. Okay, and so now one of our strategies is, once you draw the force diagram, if you have any force that is not along an axis, we need to think of components. Okay, so T2 has an x component, we'll call that T2x, and a component T2y. Okay. All right. So now when we talk about the derive equations, so if this is in static equilibrium, it's at rest, then we know that F net is equal to 0. Okay. So we can, for example, if we want to come up with, we'll actually start with T2 here. Okay. So we know that the forces in the up and down directions have to balance each other out. So we know that T2y has to equal mg. Okay. Now you can write T2y in terms of theta. If we call that theta, T2y would be equal to T2 times the sine of theta. So T2 would equal mg over sine theta. So when I talk about derive an equation for T1, m is what you're given. Physical constants basically means little g in this case. So that's one equation. Okay. We know that T1, the two x forces have to be equal to each other. So T1 has to equal T2x. Okay, they have to balance each other out. And so if we take T2x, so T1, so T2x is equal to T2 times the cosine of theta. And now we have this formula for T2, so we could substitute that in. So we could say that T1 is equal to mg cosine theta over sine theta. Okay. Another example, the constant velocity case. And again, this might be one where you want to pause for a second, see if you can draw the force diagram and derive the formula for the coefficient of friction. Okay, I will go ahead and do that now. So we have a downward force mg, got a normal force upward, got our force of 275 newtons, and because we know it's at constant speed, we have a frictional force there. So because we have constant speed, we know that F net is equal to 0. So sometimes we use like equality marks. So we know that those two forces have to be equal and these two have to be equal. Okay. So if we look at the one equation that we would have is that N is equal to mg. Another equation that we would have is that the frictional force has to be equal to 275 newtons. Now they asked us about the coefficient of friction. So if you remember the formula for the frictional force, that's equal to the coefficient of friction times the normal force. The n's can be a little confusing here, so this n is normal. That stands for newtons. So you have mu times mg is equal to 275 newtons. So you'd have, no, hope we haven't locked up here. Okay, it's doing that thing, like it occasionally does. Move those out of the way. And so we'd have 275 over mg. Okay, two more cases really quickly. And again, I'm just kind of reminding you how this works and how the strategy works. Okay. Another example. This is something a little different. I don't think we got a chance to, so let's think about this. So a plumb bob accelerometer. Accelerometer can tell you which direction your acceleration is in and how much. Okay. We're not going to worry about the how much part, but basically what we want to think of is you have something hanging from your rear view mirror. That's the idea. Okay. So this is a close-up of the bob that's hanging from the rear view mirror. So if you're just at rest at the light, and we're drawing that, you'd have mg down and a tension force up. Okay. And then, so the force equations, we know that F net equals 0 because we're at rest. And so we know that T is equal to mg. So that's the equation that we're looking at. Okay. Now what I want you to do, this is another case where I'm going to ask you to pause for a minute. I want you to pause and think about what this would look like when the person is speeding up from the light, so that's accelerating to the right, moving at a constant speed, and also slowing down, what the plumb bob would look like, and see if you can generate some equations there. So I'll give you a second to pause. And so we'll continue on here. So if you're speeding up, the plumb bob is not going to hang straight down. Okay, the plumb bob is going to be end up at an angle, if you think about that. Okay, kind of makes some sense. Has some inertia. So when we look at this, now the free body diagram of the plumb bob looks a little different. Okay, so when it comes to these force equations, so using our strategy here, okay, I've got this, T is at an angle, so I want to think about components. Tx, Ty, okay, and so what equations could we use here? If we think about this in the vertical direction, it's not moving, and so we know that Ty would have to equal mg, that is supporting the weight, and another equation we could have is Tx now would be unbalanced, so when we do F net equals ma, we could say that the net force is Tx, and that equals the mass of the bob times the acceleration. Okay. For the constant speed one, hopefully you think about how this would hang. It would hang straight down if you're moving at a constant speed. Okay, so we know that the first law applies to constant speed as well. F net has to equal 0. So we've got T equals mg. Most of you have probably ridden on an airplane before. You know, imagine it while you're on your flight cruising at constant speed. If you just hang something down off a string, it's not going to be at an angle, it's going to hang straight down. You can't really tell from that whether you are moving or not. So you could be at rest or you could be moving at a constant speed. Okay. Now think about it. For the next one, when you slow down at the light, okay, imagine this. If you just think if you slam on the brakes, you want to it feels like you want to continue moving forward. Same thing with the plumb bob. So it's going to be hanging like that. And so we'll have something similar to what we did before. And again, we'll think of Ty and Tx. And so our force equations are similar to before, what we had with that equals mg and Tx equal to ma. But what I want to point out is that now if it's traveling to the right but slowing down, the acceleration is pointed to the left. So the net force in this equation points to the left in that situation. Okay. And then this has gone on a little longer than I hoped it would. So just remember, for the inclined planes, I'll try to speed things up here a little bit. So remember, you have a normal force, you have a weight force which is acting straight down, equal to mg, and if there's usually we are just sliding down the incline, so if there's a frictional force, it usually goes in that direction. And I just want to remind you that for an incline, you want to rotate the axes. So we want to think of this axis that is perpendicular to the plane, so that's the perpendicular axis, and we have the parallel axis, and we need to find the components of this weight force. So that's the perpendicular component of the weight and the parallel component. And if you look back in your notes, you'll find the derivations. So the parallel is equal to mg sine theta. Perpendicular is equal to mg cosine theta. Okay. And then remember that you could redraw this so that now everything is at right angles to each other. So this would be the normal, weight perpendicular, weight parallel, and the frictional force. So after that, everything just works like it normally does. Okay, so the last thing I want to think about is the Atwood's machine, which is the two weights that are connected by a string with a pulley. So sometimes they're both hanging straight down. Sometimes one is on the table and the other one's hanging straight down. Sometimes it's really easier to do this with a system approach. So if we call the system is equal to the block big M, the block little m, and the string. Okay, we're going to have a frictionless pulley, massless pulley. Usually there's no friction on the table, but if we look at that. So remember that when we're talking about a system, okay, the acceleration of the system is equal to the net force on the system, or the net external force over the mass of the system. So if we look at the forces on these objects, we're going to have a tension T, a weight force little mg. This one will have a tension T. This will have a force big M, or that's the normal force, excuse me. And this one is going to have a weight force big M G. So if you look at the system, okay, the external forces, you basically decide whether each thing is internal or external. So the normal force is external. It's coming from the table. The weight force is external because it's coming from the earth, and the table and the earth are not part of that. But those two cancel out. They're going to be equal to each other. Okay, the tension forces are internal to the system. Okay, tension force of the string on the block, those are all part of the system. So those two are external, are internal, so they don't count. So if you're looking at this, the net external force is just equal to, this is the only external force that's not canceled out by anything else. So that's equal to little mg over the mass of the system, which is big M plus little m. Okay. So if you don't actually need to know what the tension is, that's kind of a quick way to do those. Well, I know this was a lot, so I will end now, and hopefully this was a help.